pair, I has to be less than j. Okay? So it's that kind of pair with this condition. All right? Now, so now let's concentrate just on two of these numbers. And ij is one of these pairs, and I is less than j. Okay? Now, so these, the upper row and the lower row, they're the same. Yeah, have a look here. They're the same set, if you like. They're just reordered. They're differently ordered. And the upper one, they are ordered numerically. Okay, here. And these, well, these are just these. Okay. Now let's take the case where this pair is a non-reversed pair. From the previous session, remember what that means. If it's non-reversed, then x of I is less than x of j. Okay. Now we're trying to prove this cross-point intersection type proof. We're trying to prove theorem 42. Okay. So let's draw a line. Now remember, you draw lines between the same numbers. So 1, 1, 2, 2, 3, 3, 4, 4. Okay. So let's draw the line. Now these two are the same, right? So draw a line between them. And now we're trying to figure out, for a non-reversed pair, will we get an intersection? Will we get a cross point or not? Okay. Now, somewhere in this list is xi. Okay. Because I mean, you know, these and these map bijectively 1 to 1, right? So somewhere in this upper list is xi. Now it's non-reversed, right? And remember, now here's where we're going to start using it. Remember that upper row is in numerical order. Okay, maybe you're starting to see where I'm going now. All right. So where in this upper row will this xi be? And we're talking now the non-reversed case. Right? In the non-reversed case, x of I is less than x of j. Okay, and here's x of j. It's here. So in the non-reverse case, this one will be somewhere to the left of this one. Do you follow that? Because that's critical, what I've just said. Right? That's the heart of the proof. Will I say it again? We're talking about a pair, right? ij pair, and I is less than j. This is in numerical order. And we've drawn a line between the xj, just like here, you know, 1, 1, 2, 2, 3, 3. And we're now trying to figure out where will this one, which, you know, if we want to draw a line between this one and wherever this is in the upper one. So this x of I will be on this line, this row, somewhere. Now it's an unordered pair, therefore x to the I is less than x to the j. So, and this is numerically ordered, remember? So that means this x of I must be to the left of this one, because this is numerically ordered. So your x of I will be to the left of that one. So we can draw the line there, and look, no intersection, no cross points, right? And that's very general what I've just said. If I and j, you know, they're a pair, I is less than j, and if x of I is less than x of j, there's no cross point, right? All right. Well, now let's do the other case. So in this case, you have a reversed pair, and can you remember what that means? It means x of I is greater than x of j, and remember this row here is numerically ordered. So with the same kind of logic, now since x of I is greater than x of j, your x of I in this row must lie to the right of this. Okay? And then when you draw the line, you get an intersection point. an intersection, a cross point. Okay. Now that's true of any pair of this form. Okay. So for each reverse pair, you get one cross point. We just proved that there, right? So for if you have n, you'll have n lines, right? There'll be n lines. Oh, be careful. I'm not talking about this n. I'm talking about the size of your symmetric group, right? So in this case, it's 4. So you have 4 lines, right? And if these pairs are coming from a symmetric group of size, let's say p, this is stop confusion, then there will be p of these lines, right? And then if you have big N reverse pairs, there will be big N intersections, cross points. So think about that, and that that's your proof. All right. Now a new topic. Given the space on the board. Now earlier sessions, I was talking about you can write permutations. This is like the full way, right? Everything's there, and you have to write 2 rows. That is the bracket notation, right? Well, there's a shorter way of doing it, and it uses the concept of a cycle, so something that's looping or cycling, right? So it's a shorter way to write a permutation. This is like the full way, the bracket format, right? Now here's an example of a cycle, and you'll see why it's called a cycle. So now these are just elements of your permutation group, the set of objects that you're permuting, right? And they'll be integers, but this is general. Now in general, remember that the vertical pairing, that's all that matters, but the order of these vertical pairs irrelevant. So if A1 maps to A2, and then A2 maps to A3, and A3 to A4 ... and then A to the n maps to A1, well there's your cycling, right? So you've got A1 to 2, goes to 3, goes to 4, goes to AN, goes to A1. So then you're back to here and you cycle. Okay, so this format here, now this is like a special case of this, right? In a sense. That cycle is said to have a length of n. The length just means how many terms in your row, and it's 1 to 1. So the length is just how many terms here. We've got n terms, so the length of this cycle is n. Right? Now we can rewrite this in a shorter way. Instead of having like 2 rows, we just have 1 row, and you write it in the following sense. You just write out 1 row, and you just say A1, A2, A3, ... AN. And when you see this, what it means is that A1 maps to A2, A2 maps to A3, ... and A to the n minus 1 here will map to A to the n. Okay? Now, let's do an example. Here's a permutation, and let's say it's, call it X, and it belongs to, let's say, S of what, 6. Right? So this is one permutation of the symmetric group of 6 objects, let's say. All right. Well, look, what?